So, good morning, everyone. Sorry for the delay. I promised you that we will go over the homework. So what we'll do is we'll actually start with the lower bound, showing why one round is not enough, and then go over your proposed solutions. Somebody asked me yesterday, so I have a one-round protocol. Can you show me an easy way to show why it's wrong, why it doesn't work? So hopefully this lower bound will give you a generic way. Anybody who gives you a one-round protocol, you can immediately explain to them, give them an example of why it fails. And again, I'll mention you can Google decentralized thoughts. This is our group blog, and you'll see a lot more details of the things that I'll be talking about today in this group blog, and eventually you'll see more work in there. So just as a reminder for people who weren't here yesterday, or just like me have a very short memory, let's recap. Our goal here is to look at consensus protocols. Consensus, basically, every party has an input. Communication is done via point-to-point channels. So there's no broadcast channel, just point-to-point channels. And what we'd like to do is maintain these three properties of liveness, safety, and validity. So liveness or termination is this property that eventually all parties must decide on a value. And once you make a decision, you cannot change your mind about this decision, right? This is kind of the basic property. The important property that captures consensus is safety. It's the fact that we cannot decide on different values. So we'd like to have all non-faulty parties decide on the same value. That's safety, and then we said, that's easy to do because you can just decide on some default value. So we want to have some relationship between the input values and the decision value. And so one way to define this is this with the validity property, and I have here two different validity properties, a slightly weaker one, which is basically if all the non-faulty start with the same input value, then this must be the decision value. And what you could sometimes want is a stronger property. So what if, the non-faulty have different values? Then you'd still like to get some sort of good property. So in particular, if you have randomization, you'd like to get this fair validity property where with constant probability, you're using the input of a non-faulty party. I will just say this is the analog of what's called external validity. So if you actually have a system where these parties that are trying to reach consensus are reaching consensus on client commands, then if these client's commands are actually signed, then this type of fair validity would give you the ability to say that with constant probability you actually use a message sent by an authenticated client. So this is kind of the high level of the three properties. And what we'll go over is this proof that you require T+1 rounds if you have T crashes. So any protocol that withstands T crashes has to have some execution with T+1 rounds. And we're going to use, so this is kind of proven in 82. We're going to use a modern proof approach from Aguilera and Twegg. So I'm going to go over some formal definitions. So they look a little bit tiresome, but because it's a lower bound, we want to make sure that we're kind of a little bit more formal in terms of what we're capturing. So we'll talk about a configuration of a system, and what is the configuration of a system? Well, each party you can think of it as a state machine, right? So a configuration is simply the state of the state machine of each party. And if the parties have sent messages and these messages didn't arrive yet, because maybe we're kind of in the middle of a round, then we'll also include in the configuration all the messages that have been sent and were not received yet. Okay, so it's basically a snapshot from above of all the system, right? You can see everything. And this is kind of a configuration. And then, we will define what does it mean that a configuration is deciding. So configuration is deciding if all the parties decided. Okay, so remember, we have to eventually have a protocol where everybody decided. So how do you know if a configuration is deciding? You look at all the parties, and you check whether they're all decided. All the non-faulty parties are decided. And we'll say they're 1 decided or 0 decided if they decide 1 or decided 0. Okay, and then this is kind of the only, it's a very simple definition, but this is kind of the only one that requires a little bit of focus. So what is an uncommitted configuration? So an uncommitted configuration is a configuration where, so we're looking now at a deterministic protocol. So the protocol, everything in the protocol is fixed, and the only choice here is what does the adversary do? And what are the choices of the adversary? Well, the adversary can crash parties, right? Remember, the adversary can crash parties in the middle of execution. And so because of that, we can talk about a future of a configuration. So if you fix a configuration, you look at all the different futures. These are all the different actions that the adversary can take. Okay, so this is basically a game for the adversary. And we can say that a configuration is uncommitted if there is some action that the adversary can take that reaches a 0 deciding state, and there is some configuration that the adversary can take that reaches a 1 deciding state. Okay, so it's very simple. It basically means that, well, you better not decide right now, because the adversary can take some steps and cause people to decide 1, and take some steps to decide people to decide 0. So this is an uncommitted configuration, and just symmetrically, we'll say that a committed configuration is one where no matter what the adversary does, the decision value is already fixed. So maybe we don't know this, and this happens a lot in these protocols where you don't even know that the decision has been made, but no matter what the adversary does, the decision value is going to be fixed. So this is a committed configuration. And so 1 committed, if it's no matter what the adversary does from this point onwards, it's going to be 1, and 0 committed for 0. So is this, any questions about these 3 definitions? Pretty simple. Okay, so what we're going to do is basically show that there has to be some state, some initial state that is uncommitted. Okay, and this is going to help us build a lower bound, because as I said, intuitively, you can't decide if your configuration is uncommitted. And so again, just a reminder, an uncommitted configuration, do I have a pointer here today? Uh-huh. Okay, wow. So an uncommitted configuration, as you see, is just one where you have both a deciding 0 and deciding 1. I'm saying wow because I have to point it this way so that it points to the so I have to kind of, yeah. Okay, so yeah, so what we want to show is that that there has to exist some initial configuration that is uncommitted. And the proof approach here is something that you've probably all seen. This is a type of a hybrid argument. So we will assume by contradiction that all initial states are committed. Okay, so what is a initial state? Initial state just says what are the inputs of all the players. Okay, so obviously if the input of all the players is 1, are we in a committed state or an uncommitted state? Exactly. So we're in a committed state because through validity, we know that if all the parties have 1, 1 must be the decision value. And so by definition, if all the parties have 1, this must be a committed state for a committed state for 1. If everybody has 0, it's the same thing. We must be in a state where everybody is committed to 0. And so now we're assuming by contradiction that all the states are committed. So not only the all 1 is committed, and not only is the all 0 committed, but all the intermediate steps. So in each step, I just flip one more party to be closer to 0 or 1. Okay, so this is basically a hybrid argument where in every step I change just one party from 0 to 1. And since you start from 1 here and you go to 0 here, then it's a simple topological argument that there has to be some place where it changes from 0 to 1. Right? This is a very simple argument. I'm saying this because later proofs use this same idea in a more complicated way. Yeah, so let's take these 2 places where it starts from 0 and then goes to 1. And so the change here is in only one party. And the problem is, and the trick is going to be that if we crash this one party, then you will not be able to differentiate if you are in the left world or in the right world. Right? So in the left world, you are committed to 1. In the right world, you're committed to 0. But the only difference between the left world and the right world is the input of one party. And if I crash this one party before it even sends a message, then how will you know if you're committed to 0 or committed to 1? Your execution is going to have to fail. I mean, you have to decide something, and it'll either fail for 0 or for 1. So this is kind of a proof by example. So again, let's prove specifically for the case that you were looking for. If you have 3 parties, that you cannot have a protocol that commits in one round. So again, there are 4 initial configurations. The leftmost one, you have to be committed for 1. The rightmost one, you have to be committed for 0. And if we assume that there is no uncommitted configuration, then there has to be 2 adjacent ones that are committed to 1 and 0. And let's assume just for example that these are these 2 configurations. It could be other configurations, right? There are 3 edges here, so we could choose one of the 3 edges to be the worst case. And so in this case, the only difference between these configurations is the value of the middle party, right? But we claim that so what is it? Yeah, so what does it mean that 0, 1, 1 is committed? It means that no matter what the adversary does, the decision has to be 1. And what does it mean that if the inputs are 0, 0, 1, it's committed to 0? It means that no matter what the adversary does, the decision will be 0. Okay? But what happens if what the adversary does in this world is crash this party in the first step? And what happens if in this world the adversary crashes this party in the first step? So then the views of all the parties will be completely indistinguishable. There will be no way to distinguish between these 2 worlds. So you will have to decide the same value, and that's a contradiction. Right, so this is this statement here. If we crash this middle party, then even though this left world was supposed to be committed to 1 and this right world was supposed to be committed to 0, they have to decide the same value. So if they decide 1, then it's going to be a contradiction to the fact that this was committed to 0, and vice versa. Okay, so now you are equipped with a way to show a lower bound, to attack anybody's protocol if they show you one-round protocol. You basically check, using a hybrid argument, where is the flip, and then you say, well, what if I crash this party at the beginning? What do you do? Do you decide 0 or do you decide 1? And based on that, you can find the contradiction. Questions about this lower bound, this attack on protocols? This is a protocol for the adversary, right? This is how you attack consensus protocols. Good. So, yeah, more generally, the proof works in the same way. So the first thing you prove is that you have to have an uncommitted configuration at the beginning. And we've seen that. This is kind of in the general form. And the next proof is basically saying that spending one more crash, we can always extend a uncommitted configuration to a round x plus 1 also uncommitted configuration. So basically, it's an inductive argument, does something very similar to what we've discussed, that extends the fact that the configuration is uncommitted to one more crash. And finally, this is essentially the statement that we've worked on, which says that if you decide if round x plus 1 is uncommitted, then you cannot decide in round x. Right? This is kind of what we've shown for the first round. And the reason is because there might be a crash, and then this will give you an indistinguishability between these 2 options. And so this is the high-level overview. If you want to look at the proof details, there's kind of a nice sketch in the blog, and read the paper. It's a very, very short paper. So now equipped with, so this is the end theorem basically says that, well, you cannot always terminate in t rounds, so that means that you must have an execution that runs for t plus 1 rounds. And again, this is just for crash failures. There is a slight nuance here that you require, let's say, t plus 2 parties, but I'm going to ignore this nuance for now. Okay, so now that you are equipped with this lower bound, you can really try to work on this quiz. So what we're going to do is show a solution with 2 rounds that solves, so we can't do it in 1 round, right? So what is the goal here? The goal here is to write a protocol that solves consensus. Everybody has input. There are just 4 parties, A, B, C, and D. They can send messages using point-to-point channels. It's all lockstep. So you send messages in round 1, they arrive at the end of round 1. In round 2, you send messages, they arrive at the end of round 2, and so on. And your goal is to get these 3 properties, right? So first, all the non-faulty decide the same value, exactly the same value. Obviously, they have to decide. They can't just decide. They can't just not decide. And finally, if everybody has the same, all the non-faulty have the same value, then that must be the decision value. Yeah, so we're going to do the same exercise that we did yesterday. Now I'm going to give you a little bit more time. You are also equipped with a lower bound, so you know you can't do it in 1 round. It's okay to do it with more than 2 rounds. You don't have to do it in 2 rounds, but yeah, and you can work either by yourself or in your table. If there's a table that thinks that they have a solution, then they can raise their hand, and we'll see who is the winner for getting a protocol like this. So I won't interrupt you, but I'll just say that one way to check your protocol is using this type of hybrid argument, to go over the states and find where is this switch from 0 to 1, because that's usually when the things become tricky. It's pretty easy to make sure the decision is 1 where everybody has 1, and 0 when everybody has 0, but in the middle it becomes the case where you have to take a little bit of care. So this slide says solution, but it's not a solution, it's just a hint. So for people who want to try to do a 2-round protocol, all I want to say is that in 2 rounds, this goes back to yesterday. There's no smart mathematics. There's no complicated things you can do. All you can do is just well, in the first round, what can you do? You can just send your bit, right? You just send your bit. That's the only thing you can do. So what can you do in the second round? In the second round, well, you receive 3 bits. What can you do? You can just send those 3 bits. There's nothing else you can do. There's no more information you can add. So basically, this is what you have here, right? In the first round, you send 1 bit, and you receive 3 bits. In the second round, you send those 3 bits that you received, and you receive 9 bits because you receive 3 bits from everybody else. So at the end, you have your bit, which is your input. You have the 3 bits that you received directly, and then you have these 9 bits that you received indirectly. And your function is a function of 13 bits. So that's well, so now if you're really good in computers, you can run a test for this, right, and just come up with a protocol. Okay, so I'm not sure it'll help, but it's a hint for some people. There might be other ways, but this is just so I'm going to make your exponential search even smaller by saying, let's look at these bits. So this is your input. This is the things that people say about themselves, and these 9 bits are what people say about what they said. And the hint I will give is that it's never about what you say. It's about what other people say about what you said, right? So people ignore what you say, but they will listen to what other people say about what you said. So if you think about these 9 bits, so what are they? So in particular, these are essentially, I receive, let's say I'm party A, then party B sends me what it heard from C and D, right? So I'm hearing from B as a witness to what C and D said. And so the hint is that you only need to use these 9 bits. You just need to look at, so you basically can ignore what people sent you, because they might be liars, right? But what you look at is what people said that they heard this person saying. Yeah, and so these pictures, what are they showing? They're basically showing, this is what B said that A said. This is what C said that A said. This is what D said that A said. And here you see the same thing. This is what A thinks that B said, what C thinks that B said, and what D thinks that B said. And so on for all the four parties. Okay, so I promised to give you one more of this. So is there any brave table that wants to propose a solution? Majority. Okay. Yeah. Good. Anybody else wants to propose majority? Okay, so that's one table out of, yes. Okay, so yeah, so I heard majority twice, so let's try majority. The trick here, though, is that, look, what we're doing majority is on this gossip graph, and the important part here is that when we talk about majority on A, we do not include what A says about himself, right? So we just say, what do people say about A, and we can take majority on that. Okay, so this is maybe the only twist or non-trivial twist here. So let's just go over the properties. So liveness obviously will just have a function, so that function will output some bit. And so what will be the protocol? So the protocol will basically be the following. We will generate these four trees for ourselves. And in these four trees, we will write in the leaves what every party said about every other party. Okay? If it's ourselves, we don't really need to make this tree, but still, in your mind, for the proof, you can imagine that you make this tree just like everybody else will make this tree. And what we'll do now is prove that if you take majority on the leaves, then the value of the root of this is going to be the same for all non-faulty parties. Okay? So all non-faulty parties will compute this tree. They might see slightly different things, but let's still hope to see that a majority will work. And what we will focus on is two different cases. So the first case is that the party that we're gossiping about is non-faulty. So if the party is non-faulty, it means that it is telling the truth. So in particular, if B is telling the truth, and let's say it had 1, then the remaining 2 non-faulty, whoever they were, will say that B said 1. Right? And if B had a 0, then the remaining 2 non-faulty said 0. So if we take the majority vote, we will be fine, because the Byzantine party will say whatever it wants. There's 2 people that are saying something, and then a third which can say something else. It doesn't matter. The majority value will be what B said. So again, if the top node in this tree is non-faulty, then taking a majority will be fine. We're basically masking the faulty party. So it could be that we see a different gossip from the faulty party, but all of us see 2 people saying that B said 1. And so the majority will be 1 for all of us. So that's the first case. And the second case is if the party that we're gossiping about is faulty. So if B is faulty. So if B is faulty, why are we still okay? Why do we get consensus on the value of B? Sorry, because it's 3 out of 4? Yes. Yes. No, I want to say something stronger. I want to say that even this one tree, we will all agree on its value. So I don't want to mask this value. I want to say, even if B is faulty, when we compute a majority, all non-faulty will compute the same value for B. So that's the question. Why is this true? Yeah. So this is what you want to say? Good. Yeah. So essentially, if B is faulty, then all these other parties are non-faulty. So if they're non-faulty, they will say the same thing to everybody. So all the non-faulty will see A, C, and D say exactly the same thing. No matter what B told A, C, and D, A, C, and D are non-faulty. So when they gossip, they will say exactly the same thing to all the non-faulty. So basically, by ignoring what B said about himself, we get consensus on what B said. Okay? Is a question? Yeah, so B is the faulty one, but we still reach agreement on what his bit is. His or her bit. Yeah, so I think, so the question was if you have a larger alphabet. So I think, I think what you need to do is if there is a majority that have the same value, then you take that value. But I want to make sure that I'm not mistaken. Yeah, no, but there's a way to do it for the full value. I think if everybody says, yeah, you're right. Good question. I don't want to. I don't have an immediate answer. But there is. Yes. Yeah. Remember, this was the game here. 4 parties, 1 malicious. So just last thing is that now that we reached agreement on every tree, on every root of every tree, even if the root is malicious or honest, all the non-faulty reach the same value. And now we can take majority on all these 4 bits. And by taking majority on all these 4 bits, we obtain the validity property. Because if all non-faulty had, let's say, 1, then everybody would see at least 3 1s. And if all non-faulty had 0, then we would see at least 3 zeros. So the majority function will again give you validity. So questions about this, this upper bound? You have to decide. Your function has to, so you can choose your protocol. It can decide either 0 or 1. These are 2 different consensus protocols. They are still valid. But yeah, it shows you that there is some degree of freedom. Sometimes you want protocols that prefer 0 or prefer 1, and in some cases it actually matters. Exactly. Exactly. Yeah, so everybody will see 2 and 2. Yep. Anybody's solution was similar to this, or good. Okay.
What about the majority of everything you have?
Oh. So you're saying taking the majority of everything. So I think the problem there is really that you need to ignore a faulty party. Because if you take what the faulty party says about itself, then it can cause people to see different values. And so you won't have this property that the tree will be computed for everybody. So it maybe there's a possibility to use this bit, but at least naively, it could be that you see 1 bit more and I see 1 bit less. But if I had, I actually like hand checking a counterexample, I can't do it online. But my guess is that it won't work.
If you're a top player and none of them is in team, so 2 have 0 and 2 have 1, what is the majority generate?
Yeah, so your protocol can decide, this is the same question, your protocol can decide whether it will prefer 0 or 1, and in both cases, all you care about is agreement. Validity should be fine. It's a good question. So we have 10 minutes, and or maybe a little bit more because we started a little bit late. And what I'd like you to do is, so is there any questions about this upper bound solution, this approach? So you get to choose between two different riddles. One riddle is the simple one, which you tackled yesterday, and now I want you to use the same techniques to obtain a 2-round protocol. Again, if you receive a 1-round protocol, then use your lower bound that you've learned in the first half to prove yourself that it's impossible. But build a 2-round protocol for 3 parties. This time it's not Byzantine, but omission. So this is if you feel you're confused about this upper bound. If you are more adventurous, then try to look at 7 parties and 2 malicious. And so this is an extension. Now you will fail in 2 rounds, but you need to give a 3-round protocol. So you can choose either the more conservative riddle or the more challenging one. And so there's about 10 minutes, and at the end of the 10 minutes, somebody will be able to say, using maybe this type of approach, how you would solve these riddles. Benny, so thinking on my feet now, so the rule will be simply if there is something that receives a majority, use it. Otherwise, use a default value. And that will be the multi... Yeah. Yeah, if you get a non-majority, you know this guy is is a liar. The only question in these protocols, again, so it's 2 rounds, full information. We're talking about the omission, the omission case. You receive even less bits, right? So you receive 2 bits and then 4 bits in the next round. The only question is when you take some sort of function, let's say majority, of say party A, do you look at what party A said, or do you listen to what B and C said about A? Right? So we can use the same trick. If it works for Byzantine failures, maybe it also works for omission failures. So we would have the same case here, except that this tree is even smaller. There's just 2 nodes. Only B and C talk about A. Okay, so if A is non-faulty, then we know that at least one other non-faulty will report the value, and maybe the other will be silent. So at least we will get one value that is correct for A. And we also know that if A is faulty, then no matter what, B and C will hear something about A. Right? So either they heard a message or didn't hear a message, but B and C will report this fact about A to everybody. So again, the main trick here is when you're taking majorities about A to ignore A, to actually look at what B and C say about A. Okay, because if we actually take into account what A says about himself, then you and I might not see the same thing about A. But if we take into account what B and C said about A, if A is faulty, then B and C will say exactly the same thing to both you and me. Right? And if A is non-faulty, then again, just taking here a function that says if there's any value, use this value, would be fine. So this is kind of the solution for the omission, the same idea. And for the 7 parties, you need to basically extend this tree. Right? So you extend this tree of gossiping where every party talks about what every other party said about what everybody else said. So we basically have a deeper tree. And what I would like to do is, you can spend time during this 15-minute break that we have, right? to understand the details of the 3 omission and the 7 Byzantine or the 4 Byzantine. But after the break, I would like to zoom you back to a more complex protocol. This is the protocol that we've seen yesterday, and so I will go over this protocol again to remind you of it. But again, what is this protocol? So here we are trying to solve, again, in the information theoretic setting, for a Byzantine adversary that controls less than a third. We're not trying here to get exactly the optimal number of rounds, but we are trying to provide a framework that will allow us to have a constant expected number of rounds once we use randomization. And in order to get this, we're using this primary backup approach. Again, you're seeing this is very different than the protocol you've seen now, which is very symmetric. Everybody essentially computes the same thing. Here, this is a very asymmetric protocol where there is one primary that's sending messages, and then basically we do this all-to-all sending several times, and I'll go over the details of this protocol. And so after the break, this is what we're going to zoom back into. So you have 15 minutes to think about this small problems of 3 and 5, and then afterwards we'll go back to this more general solution.